So there's 10 to the minus 30 grams in every cubic centimeter of space, so small and not zero. Every calculation we do suggests many orders of magnitude larger. And theoretical predictions, the cleanest theoretical prediction is that the energy density of the vacuum should be infinity to the fourth power. Not just infinity, but infinity to the fourth power. Everything that we can think about the vacuum has a much, much, much larger energy density than what is observed. Finally, secret 6 of nothingness. Nothing matters. It's the energy of nothing that will determine the ultimate fate of the universe. If there is dark matter dominant in the universe, the ultimate fate of the universe will be either a universe that expands forever, decelerating with the velocity decreasing with time, or perhaps if there's enough dark matter, the universe will reach a maximum volume and then collapse into a big crunch. But if dark energy dominates, then the universe will expand forever at a faster and faster rate, and the galaxies that we see around us today eventually will expand so far away from us that we won't be able to see them. Our galaxy will be alone in the universe. That's why we have to do astronomy now. Those galaxies are getting farther away. We gotta look at them now. So this connection between microphysics and macrophysics is something that really appeals to me. Now, humans are mid-size in the universe. The scale of our common everyday sensory experiences are about 1 meter, about a yard. The smallest scales that we can sensibly talk about today are 10 to the minus 26 meters. The largest scales we can sensibly speak of today are 10 to the plus 26 meters. The scale of our everyday experience is the geometric mean of them. We do not experience in everyday life the quantum nature of microscales. Nor do we experience relativistic effects of speeds near the velocity of light. Humans, midway between the largest and smaller scales, evolved to perceive reality not as it actually is, quantum mechanics, general relativity, but merely as required to survive in our environment. As Hawking said, we are just an advanced breed of monkeys on a minor planet of a very average star, but we can understand the universe, and that makes us something special. So let me wrap up by concluding what I'd like you to take away, that 95% of the universe today is a mystery. 95% dark matter and dark energy, and we don't yet understand it. Now, I mentioned that I thought modern cosmology began with Einstein. Einstein was, according to Time magazine, the person of the 20th century. What would Einstein think if he knew that 100 years after he launched us into modern cosmology, 95% of the universe will be a mystery? I think he would be happy. He said the most beautiful thing we can experience is the mysterious, the source of all true art and science. And those to whom the emotion of mystery is a stranger or as good as dead, their eyes are closed. The universe today is 95% mystery. I think Einstein would be happy to know that. Although today it's a mystery. Scientific mysteries are solved. There will be a new Einstein who will solve our cosmic mystery. Somewhere out there, is the person who will be the person of the 21st century who will solve our cosmic mysteries and undoubtedly make cosmic mysteries of their own. Thank you very much for coming out today.
Okay, we have time for some questions, so if you could raise your hand and I'll bring around the microphone. Let's see, anybody on this side? Oh.
How does the black hole interfere with all this? If everything's expanding, the black hole's pulling everything back in.
Right. That's a good question. Thank you. I guess everyone heard the question. How do black holes fit into this picture? There has been an idea that black holes could be the dark matter that's holding everything together. And originally, it was thought that if black holes are the dark matter, they must be the mass of the sun, 5 to 10 times the mass of the sun. And those were ruled out by observation. But recently, in the past 2 years, from gravitational wave discoveries, scientists have discovered the existence of black holes that are 30, 40, and 50 times the mass of the sun. No one really anticipated that these things would be around. And people have proposed that these really large black holes, whose origin we really don't understand, could be the dark matter. This is a field of active research now. So dark matters, black holes may play a crucial role in this idea. Thank you.
So if dark matter interacts with regular matter gravitationally, why is it distributed in a different way around galaxies?
So that's a good question. So that's illustrated here. The galaxy is really much smaller than the dark matter. The idea is that originally when the galaxy formed, the dark matter and normal matter that would end up being stars and things that we see were all mixed together. Then they collapsed gravitationally. Now the dark matter did not interact very much at all, so it collapsed and started oscillating and remained sort of fluffy. The matter that we do see, as it collapsed, it interacted and radiated energy and fell deeper into the potential well. So the stuff that interacts and radiates and loses energy can fall into the potential well. The dark matter remains fluffy.
So could you have a dark matter black hole? If it's interacting with itself gravitationally, couldn't it collapse?
The only thing that the only thing that describes it, once a black hole forms, you can't say what's in it or how it was produced. You can only see its mass. So in fact, maybe you could form black holes just out of dark matter. And again, black holes formed by normal matter might be the dark matter. I don't know whether that made, now that I listen to it, I don't know. You get it, right?
Got one back here in the back.
Dr. Kolb, so you mentioned with quantum vacuum fluctuations that it's based on the uncertainty principle. Isn't the uncertainty principle based on momentum and position? So how does that work?
Based upon what, sorry?
Momentum and position, sigma
Yes.
x, sigma p?
Yes.
So how does that work for quantum fluctuations in a vacuum, since there isn't a particle there originally to determine that uncertainty?
Are you a physics major?
Yeah.
Sorry?
Yes, sorry.
Okay. So one of the things you learn in physics classes in quantum mechanics is that if you have a quantum harmonic oscillator, then there's a 0-point energy associated with that. He'll explain that to you later. So there's a 0-point energy associated with that. And in quantum field theory, all of the elementary particles essentially are described as harmonic oscillations of the field. So at every point in space, there's a harmonic oscillator that is for every type of fundamental particle, and there's a 0-point energy associated with that. The rest of you are not responsible for that, I'm afraid.
Thank you.
I see a question back there. Why don't you stand up and speak up?
He's
Oh, okay, he's coming.
So if you said the space-time fabric thing, like the stars like warp or dent that, are black holes like holes in that? Or if they're that massive and like, yeah.
Yes, good question.
Yeah.
Black holes bend in warp space because they're massive, but more than that, inside of a black hole is something we call a singularity. That's where space and time cease to exist. So there will be a point inside of a black hole where space and time are not defined. So a black hole is a really beautiful object. You know, it not only on the outside disturbs space and time, but there's a point inside the black hole where space and time do not exist.